Yeah, all I'm saying is you've got to work harder than me in some sense. But I wouldn't, maybe that's possible. So we've kind of come to a natural break, but I still have an hour left, and so I'm just going to start. I think we have to start. We've got to get on. Global fields are harder than local fields anyway. So part 2. The global Langlands conjectures. So it's hard to make sense of the global Langlands correspondence. I've told you pretty much all I know about the local correspondence, in fact. The global correspondence, this is certainly much nearer to the kind of stuff that I actually know something about. But this is, hopefully the first lecture or so will be relatively straightforward. I don't know. So global means now we're going to do number fields. So, of course, much harder than local fields. On the other hand, probably far more familiar objects for most of you. So we don't need K anymore. So now let's have in this part, K will be a number field. Right? i.e. a finite extension of Q. And now it would be nice to begin with some kind of overview of what we're doing, but as probably some of you have realized, I'm writing these lectures on the fly. So I know something about where we're going, but I don't quite know where we're going to get to. So what we're going to do is I need to talk about, I'll start by talking about global Galois groups, right? About the structure of gal L over K, where L over K finite, right? Finite. Galois extension. So this is just any course you've been to on Galois theory, at least any course you've been to that I've lectured, these are the examples of Galois groups you see all the way through are finite Galois extensions of number fields. So these are very natural examples. But at least in my university, somehow the Galois theory course runs the semester before the algebraic number theory course. So you can't use the tools of algebraic number theory to really start decomposing this Galois group. So I'll start by putting those sorts of things together. So we need to talk about the structure of that global Galois group, and in particular some way of referencing the elements. And I want to talk about its relationship, and in particular its relationship to local Galois groups. I've decided I'm not going to do what I tried to do in the locals. In the local section, I wanted to look at kind of local extensions which were infinite but maybe only finitely ramified. I'm going to sit with finite extensions. I just think it's easy to understand. I think in some sense I'm beginning to regret what I did for local fields. So we'll do that, and we'll take limits. We'll take limits. We get some structure on gal k bar over k. Okay. The next thing I want to do is I want to talk about global representations of this global Galois group. Right? So we had a local Galois group, and then we had a local Weil group. So there is a global Weil group, but it's much more complicated. And what's worse is that in the local situation, the Weil group wasn't quite the right answer because we needed Weil-Deligne representations. In the global case, the global Weil group is not quite the right answer either, and we need to replace it with the global Langlands group, and nobody knows what that group is. There's actually not a definition. So the global Langlands correspondence says that there's some relationship between representations of GLN of some group related to some global field and n-dimensional representations of the global Langlands group. So this conjecture is unprovable because we don't, not only is this supposed to be a natural bijection, but we don't even have a definition of at least, of one side. So you can see why you begin to see why this is called a philosophy, why people refer to the Langlands philosophy. And it's quite well chosen. It's quite well chosen name because some parts are very well defined, and some parts are just you have to be a little bit of a dreamer. So we'll take structure on K-bar of K. So the kind of the global analog of I know in America, but I'm going to write it in an English way. The global analog of a Weil group, of a Wedelin representation, may well be maybe something like a representation of global Langlands group, right? There. And I think I read in a paper of Arthur that in 50 or 100 years' time, or whenever, when we finally prove all the local and global Langlands conjectures for number field, maybe, I don't know, maybe 10 years' time. Look at what Schultz is doing. If at some point in the future, when we prove the global Langlands correspondence, maybe the very last theorem will be the global Langlands group exists. That might be somehow. It's not something that it might be the case that rather than constructing it and proving theorems about it, we might have to wait till the very end before we've even constructed it. Maybe we'll construct all the representations of it first, and then we'll say, ha ha ha, by Tanarkian formalism. If you construct all the representations of a group, then you can construct the group, right? That's a theorem. Tanaka-Krein duality or something. So as you can see, it's going to be a little bit tricky talking about examples of representations of the global Langlands group because we don't know what the definition is. But what we saw in the local case was that we had a source of Wedelin representations, and they were L-adic representations of a Galois group, right? However, we still have L-adic representations of gal K-bar over K, right? And in the local story, I said, these exist. I said, Tate module of an elliptic curve. I maybe said, Tate module of an abelian variety. I maybe said, L-adic et al. Cohomology of a smooth projective variety. But there's a machine that spits out representations to GLN of an of QL. And that machine works globally as well. So we can get L-adic representations of gal K-bar over K, and so maybe these are a working definition. So this is a kind of a working definition of the right-hand side, of the row side, right? And then the pi side, that's where we see automorphic representations. There. Now, the global Langlands philosophy is that every single automorphic representation, obviously one of the key things I'm going to be doing in this part is defining these things. The global Langlands philosophy might say something like the following. Given an arbitrary automorphic representation of GL2 over K, I should get some two-dimensional representation of the global Langlands group. So that's very difficult to make precise. But you see, locally, remember, I said, given a L-adic representation of this Galois group, we could, by some proposition of Grothendieck, we could construct a Wedelin representation. But we don't get all Wedelin representations that way. There was some L-adic unit issue. So these L-adic representations of gal k bar over k, these are going to give us a source of automorphic representations, but maybe not all of them, you see. And what I believe should be going on for a general group is that somehow L-adic representations of gal k bar over k that have some nice, that are algebraic in some sense, they have good p-adic Hodge theory, they should match up with automorphic representations which are algebraic. And in this, for an arbitrary connected reductive group, that might actually be a conjecture of me and Toby G. But I'm not remotely an expert in this area. And so it would not surprise me if all the conjectures in that paper were known to the expert. In fact, I'm pretty convinced that all the results in that paper I wrote with Toby G were known to the experts, but different bits were just known to different experts. So there was no expert that knew all of it. That was what we decided. That was why we wrote the paper. Because every single person you talked to knew about 3/4 of that paper, but it never occurred to them that the last bit they hadn't fathomed out. Being known to the experts is a very dangerous thing. I once wrote an entire paper about level lowering for mod 2 representations. And when I finished writing it, I realized that I hadn't had a single idea. It was a zero-idea paper, but it proved a result which at the time was of great technical importance. And I emailed Ribbett and Taylor when I realized I'd done it. I was in Oberwolfach, I remember exactly where I was. I emailed them both and said, this technical result, which Richard, which you know that we need, this technical result is a triviality. It just follows from results in the literature. And both Ribbett and Taylor responded instantly and said, I thought the problem was here. And they said they thought the problem was in two completely disjoint parts of the argument. So each one of them knew how to solve the problem that the other one thought was the theoretical obstruction to proving the result. So the whole argument was known to the experts, and yet I still got a paper out of it. It was kind of funny, because no expert knew all of it. And I kind of feel that the same is true here. I made a conjecture with Toby G about this story. But I'm not going to talk about that conjecture with Toby G, because for GLN, this is historically much older. So for GLN, this is a conjecture of Laurent Clausel, right? So kind of uncheckable conjecture. Uncheckable conjecture is that all automorphic representations pi, let's say for GLN, all automorphic representations for pi should correspond to n-dimensional representations of a group that doesn't exist, of a global Langlands group. Okay? So that's impossible to check because we don't know what the global Langlands group is. But there's a kind of a checkable conjecture. And that's the algebraic automorphic representations. Pi of GLN over K. These things should correspond to, motivic n-dimensional representations. Nice, well, families of nice, let's use the correct terminology because I'm going to talk about it somehow. Let me just write. Maybe now's not the time to get into this. Nice representations rho from gal k bar over k to GLN of QL bar. So nice means whatever. Unramified outside a finite set. Okay, I've said it. Unramified outside a finite set. And some good p-adic Hodge theory. De Rham at P. The clever thing, and then there should be some motives here, right? There's the triangle, as Frank would call it. So that's what we kind of believe. So the uncheckable conjecture, one can attempt to check it for GL1, actually. may be checkable. Maybe this is checkable for GL1. The reason I think this uncheckable conjecture might be checkable for GL1 is that to figure out the one-dimensional representations of the global Langlands group, all I have to know is what the abelianization of the global Langlands group is, right? Langlands group. If I the global Langlands group, I get something which I know what it is, right? It turns out to be K star modulo A K star, right? I'm going to spend some time, that's an Adele group. We're global now, so we're going to see Adeles. So I don't know what this global Langlands group is, but if I abelianize it, I should get this. So actually, for GL1, this is going to be checkable, because this is a group that I have a definition of. So I can look at one-dimensional representations of this, and one-dimensional representations of something over here, and there's a chance, right? So we have to do global class field theory, right? So for n equals 1, we'll find that the uncheckable conjecture will turn out to be global class field theory. So I'm obviously, just like in the local case, I'm going to explain what global class field theory is, and then I'm going to say we'll be able to reinterpret it in this way, but then, after a while, we're going to run into problems because we're not going to know what the Langlands group is. But this conjecture here, which should be some kind of subset of this conjecture somehow, here's an example of the problems we're going to run into. Locally, I said, if we have an L-adic representation of our group, then by some proposition of Grothendieck, we can get a Wedelin representation of the Weil group of K. So wouldn't it be nice if we had some global equivalent, given an L-adic representation of our global Galois group, maybe we can get a complex representation of the global Langlands group? Well, of course we can't, because we haven't got a definition of the global Langlands group, you see. So there are real obstructions. Even if we check this checkable conjecture, we're still a long way from proving the global Langlands philosophy, because we still don't know what the global Langlands philosophy says here. But when people talk about the global Langlands correspondence, sometimes they're talking about this, but sometimes they're talking about this. It means more than one thing. And this we can do. This we can maybe talk about. So this is where we're going. And one nice thing about the global Langlands conjectures is that in some sense they should be compatible with the local Langlands conjectures. And in this situation here, you see, so what does it mean here? Here it means that my global Langlands group should somehow contain the local Wedelin groups. And an n-dimensional representation of the global Langlands group should give me an n-dimensional representation of a local Wedelin group. And again, that's just the kind of thing, we can't do it, right? But what's for sure here is, given a global L-adic representation, we'll be able to restrict it to the local Galois groups and get local L-adic representations. And then using that proposition of Grothendieck, we'll be able to get local pies, and we'll be able to hope that our global pi is made out of local pies. So this picture here is going to be much more concretely related to the local stuff. So this is in some sense, this is what I felt my main job was when I came here, is to give you some kind of feeling as to what the local Langlands correspondence was, and then give you some kind of feeling as to what this picture says and how this picture is related to the local story. So for n is 1, we'll find the uncheckable conjecture is global class field theory. And so for n bigger than 1, we're kind of stuck. Maybe I should remark that for Galois representations which become abelian after a finite extension, we could perhaps do something. But for the Tate module of a random elliptic curve, for a non-CM elliptic curve, we can make something here, but we can't make something here. So we have to stay in this algebraic picture. And I don't know if this is worth mentioning, but I have a dream, right? And my secret dream is that these algebraic automorphic representations of G ln n of k, they're of course a subset of all the automorphic representations of G ln n of k. But I believe that the algebraic automorphic representations of G ln n of k should somehow be a subset of a new p-adic space of p-adic automorphic representations of GLN over K, and I don't have a definition for that either, and nobody does. So here's a dream. Do these live in p-adic automorphic representations of GLN over K, or whatever, or some arbitrary connected deductive group over K, whatever generality you want to work in. So there's some I don't even have a definition here. It's just as bad as this, right? There's no definition of a p-adic automorphic representation in this generality. And maybe these should correspond to rows to GLN of QP bar with I'm not demanding that my p-adic automorphic representations are algebraic, so I'm going to drop something here. Maybe drop Durham or something. Right, because Durham is some kind of assertion that this representation is nice and algebraic at P. So maybe I drop Durham. So there's some these are extremely vague ideas, but I'm trying to convince you that, I'm trying to tell you what's going on in my head. So that's maybe what the story should be. But as I say, a lot of the stuff is, one can't even work on it because we're missing definitions. We're missing a definition here, we're missing a definition here. And so that picture with that triangle up there, at least, we don't even really know what a motive is. But at least those top left and top right, we know what they are, right? Here's my job. Top left, top right, these are concrete things. I'm going to explain them, right? So that's job number 2. Job number 1 is to explain global class field theory and how it fits into the story. So that's what I'm going to do. So we're going to do definitions of that very top right-hand board. Algebraic automorphic representations, nice Galois representations, and how it fits in with the local story. And that will take a week, and then we'll be done. And then you can go back and tell all your friends about my dreams. Oh, look at this. Whole new chalk. Right. Oops. I should pick that up before I tread on it. Okay, so that's enough waffle. Let's do some stuff that you all know already. That'll be nice. When do I finish? 9:30 to 10:45, and then 11 to 12:15. Right, so I have about 40 minutes. So let's go. Let's have K over Q finite. So this is Galois, right? Galois groups. K a finite extension of Q. Of course, K equals Q is a perfectly good example, right? So K contains the integers in K. And now in contrast to the local field setting, in the local field setting, this is a discrete valuation ring. It has one non-zero prime ideal, and there's the only prime going on. In this setting, if K is Q, then e.g. K is Q, the integers of K are Z. And we see a huge difference already. Z's got infinitely many primes. So we can pick one, right? So let's just choose 0 not equal to P, a prime ideal, and hence maximal. A prime ideal of the integers of K. Great. Then, of course, OK modulo P, this is some residue field. And this is a finite field. Oops. So there's some notation. And now, if you've seen the definition of the p-adic numbers, then one way of defining them is by completing the rationals with respect to the p-adic norm. And one way of defining the p-adic integers is completing the integers with respect to the p-adic norm. And that works in more generality here. So if you haven't seen this before and you're a little bit uncomfortable with it, just pretend that k is the rationals. Okay? We can complete k at p, as it were. That's what. So here would be one way of doing it, e.g., we can define OKP to be the limit of OK mod p to the n. So this would be taking some limit of z mod p to the n as n goes off to infinity and getting the p-adic integers. And Kp is the field of fractions of OKP. Oops. So that would be one way of completing k at p. So this is the completion. This is k completed at p, right? Or another approach. Would just to be to define. We just use. It's nice to know. It's nice to know about fractional ideals and principal fractional ideals. So here's another approach. For p is fixed, right? So p fixed. And if I just take some random lambda in k star, then I can look at the fractional ideal generated by lambda. Then lambda OK, this is a fractional ideal of k. This is a finitely generated submodule of a finitely generated OK submodule of k. And any fractional ideal factors as principal fractional ideals. Therefore, factors as kind of p to some number, what would be a good notation for that number? I guess a good notation for that number would be Vp of lambda, right, times ideals, other prime ideals to various powers. This is like taking a rational number or an integer and writing it as a power of p times something prime to p. So you see, there's my Vp of lambda. So Vp of lambda is my, you see, for local fields, there's just one map V. I called it Vk, right? So this Vp is now mapped from k star to z, right? But I called it Vk locally, so here it depends on a choice of p, right? So we can define a p-adic norm, right? A norm on k by the norm of lambda. Sorry, the norm of 0 is 0, and the norm of lambda is just going to be, well, it's going to be some small rational number, some small number to the power of Vp of lambda, and by the local, I'm going to go with the same conventions we had before, right? It's going to be Qp to the power of minus Vp of lambda, right? Where Qp, this is the size of Kp. So just the same normalization conventions as I did in the local case. So there's a norm, and of course, the norm. Once you have a norm, you have a metric, right? So the norm on k gives us a metric, right? The distance from x to y is just the norm of x minus y. Okay? And so now I have a metric on this space, and I can complete, right? Complete k with respect to this metric, and I get Kp, and that's a local field. And so it's a local field, so it's a finite extension of the p-adic numbers Qp for some prime number p. What is this prime number p? So Kp is a finite extension of Qp where P, what is P? So the idea is, I look at this, remember I started off with a prime ideal curly P of the ring of integers of K, but the ring of integers of K certainly contains the rational integers, so I can intersect my prime ideal with Z, and the pre-image of a prime ideal is always prime, so this is going to be prime, and it turns out that it's non-zero as well, and generated by a prime number P. So there's some hopefully very familiar material. But at the end of the day, the point is, given a prime ideal in the ring of integers of K, I can complete. I mean, I guess it doesn't matter if it's not familiar at all. The reason I need to know this is because it's going to give us some structure on these Galois groups, right? So now let's let L over K be a finite extension. This is a nice way to finish the week, isn't it? This is hopefully relatively straightforward material. So now let's say, now say L over K is a finite Galois extension. I mean, I guess the reason it's nice is somehow because even if you don't know this stuff, it somehow looks like it might just be a finite amount of work to understand it. Whereas if you kind of get lost at the end of the local Langlands stuff, then this is sort of very complicated machinery and it might take a while to get on top of it. So let's say I've got a finite Galois. So K is always a number field, right? So L is a number field here now. I have number fields. Right? So in your abstract Galois theory course, you get a finite group, Galois group, Gal, L over K. And I want to talk about representations of that kind of group, and I want to really, get into, I want to understand abelian Galois groups when I'm doing class field theory, which is the study of abelian extensions of local and global fields. So I need to kind of get my hands on this global Galois group somehow. And this stuff here, these observations I've just been making, it'll turn out I'll be able to use these in some strange way to get a handle on this global Galois group. So here's how this works. So let's say P is as above, right? So a non-zero prime ideal. Okay? Then we've got this Galois group L, right? So P is a prime ideal. So sorry, we've got this number field L, right? P is a prime ideal of K, right? And now OK lives in L is a finite extension of K, so the integers of K live in the integers of L. And we've got my prime number down here, my prime ideal down here, but of course it might not stay prime, right? POL. And this is just a non-zero ideal. This is a non-zero ideal of OL. Might not be prime anymore, right? For example, if K is the rationals and this curly P is just the prime number P, then P is going to be prime number in the integers. But if I let L be something like Q root P, if I throw in a square root of P, then P used to be a prime number here, but in the integers of Q root P, P is clearly not a prime, it's a square, right? Because I've got a square root of P. So P times OL, I'm just telling you the basics of an undergraduate algebraic number theory class. P times OL is an ideal, but it might not be a prime ideal. And so I can factor that prime ideal. Sorry, I can factor that random non-zero ideal as a product of prime ideals. Okay? So POL factors as P times OL into primes, right? Into primes of L. So P times OL is, I need notation. I can't remember thinking of good notation. Oh, I didn't. Let's call them capital P's. It's kind of P1 to the E1, P2 to the E2, dot, 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 PG to the EG. There. So here the capital PI, these are prime ideals of the integers of L. So there we go. P might not be prime anymore, but it's factored. So here we have what I teach the undergraduates when I'm teaching them Galois theory. We do examples of Galois groups. And here we have what I teach the undergraduates when I do algebraic number theory. When I do algebraic number theory, I can't really assume that they know what it means for an extension to be Galois. When I do Galois theory, I can't really assume that they can factor ideals into prime ideals. That kind of needs to be fixed, really, doesn't it? But that's the current situation in my university, at least. We don't want to demand that people have to have been to one course to do the other. But hopefully, most of you guys have been to both of these courses. And so I can tell you, right? Gal L over K. So here's the kind of the missing stuff that I'm not allowed to tell our undergraduates, right? Gal L over K. This is an automorphism group, right? That's a group, and it acts on L, right? It acts on L, and therefore it acts on OL, because OL is an intrinsic part of L, right? It's the algebraic integers in L, right? So it acts on K. I mean, it acts trivially on K, and hence on P, right? So it fixes P, it acts on OL, and therefore it acts on, therefore it fixes the ideal. Not pointwise POL, right? As a set, not pointwise. This Galois group is moving elements around, but if you look at the set POL, if you have something in this set, then Galois will move it to something else in this set. So Galois moves this thing, and so it acts on this factorization, right? If sigma is in Gal L over K, right? Then sigma of pi, so pi is above one of these prime ideals, is a prime ideal of OL, right? Pi is a prime ideal of OL, so sigma of pi is a prime ideal of sigma of OL, because sigma is an isomorphism, and sigma of OL. And of course, pi divides p, right? Pi divides p, and therefore sigma of pi divides sigma of p, which is just p again. And so what I'm saying is, just by general functoriality, right? Just thinking about the fact, I've mentioned this to a couple of people. This is always worth mentioning, right? Sigma, you can think of as an isomorphism, right? It goes from L to L, right? But a really useful way to think of, let me just make, this might be the most, here's an observation that's sometimes useful. If I've got two random objects, X and Y, objects in mathematics, right, just defined by whatever, by axioms, axioms and, with structure, whatever. Two algebraic structures, right? Topological spaces, or whatever, groups or something. And let's say I've got some isomorphism, right? From X to Y, an isomorphism. By which I mean a bijection that preserves all the structures, like commutes with all the axioms. So, for example, a homeomorphism of topological spaces, or an isomorphism of rings, right? And then you have some calculation, then you have some kind of star equals a calculation, right? A calculation of some kind in X. maybe a theorem, or maybe, maybe an invariant, or maybe some kind of object. You do some calculation, a mathematical calculation that just involves taking elements of X and using axioms or structures or whatever. You do some kind of calculation X, then of course, because this calculation only uses the definition of X, the way that the mathematicians have defined X, you can just apply I to the calculation, right? I of star is some equally valid calculation in Y, okay? So for example, if X is a topological space and you have some kind of cool invariant of this topological space, for example, the number of connected components or the dimension of some homology group or whatever, and if Y is isomorphic to X, then that calculation will go over and you can calculate the corresponding invariant for Y and you'll get the same answer because it's isomorphic. Or if you have some kind of substructure of X defined in some canonical way, then you hit everything with I, and you'll get some substructure of Y, right? And this is called transport. This is called something in French. Deligne calls it transport de structure, right? And it's a completely trivial observation, okay? But it's important for sometimes. Mathematics is about giving the right definitions or thinking about things in the right way. And so it turns out that sometimes turns out that if thinking clearly about that trivial observation, that if X is isomorphic to Y, then anything you can do with X, you can do with Y. In the particular case, where X happens to be equal to Y, well, if X equals Y, this is kind of completely ridiculous because then I is the identity map and the calculation becomes the same calculation. But no, I don't want to do the identity map. And I is not the identity map. Right? Can sometimes really help. It could just help you. Okay. And the example I'm thinking of course, e.g., X equals Y equals L, and sigma equals I is in gal L over K. What I'm saying is we have L and we have L, and we have an isomorphism from L to L, and sometimes it's actually a good idea to let one of the L's be called something else and just forget that it's equal to L. We could maybe call it M. And then forget that sigma can be some complicated element of a Galois group. Just pretend that sigma is an isomorphism between L and M. And then you see what's happening now is that L is my number field, L is also my number field, sigma is Galois. If I factor some ideal into prime ideals here, and I factor the corresponding ideal into prime ideals here, then I will give us will identify one factorization with the other factorization. So here's my factorization of P. There's a factorization of an ideal downstairs into prime ideals here. And what I'm saying is, now let's hit it with Galois. What I want to explain to you is that if I say, now let's hit everything with a Galois automorphism, what I want you to be able to realize is that it's completely formally obvious that when I hit this factorization with an element of gal L over K, this stays the same, and this stays the same, but somehow Galois must be permuting it around, right? So Galois must send P1 to P3, and E1 must be equal to E3, and Galois maybe fixes P2, and it sends, it permutes the prime ideals around. But what I'm saying is that's obvious. You don't have to do a little calculation to check that sigma of P2 is one of the primes dividing P. You just think about it like this, and it's kind of formally completely obvious. So I've just argued that sigma of pi divides p. But what I'm saying is actually you don't have to argue that sigma of pi divides p. I'm saying it's true by transport de structure. You see. So sigma of pi divides sigma of p. Right? In particular, gal L over K acts on the set P1, P2, up to PG of prime ideals above P. Okay? And now the basic fact, not that difficult to prove, that this action is transitive. There's only one orbit. And as a consequence, all the EIs are the same. A corollary. All the EI are the same. And it also means, in some funny way, that all the PI are isomorphic, right? So corollary again, so corollary, kind of L, this completion LP1 is going to be isomorphic to LP2, isomorphic to LPG, right? You see what I'm saying? We don't have to kind of carefully check all these things. I'm just saying that I constructed, you know, this is the same construction. I went from K to K completed at P. I'm completing L at the prime ideal P1, and I'm just saying completion of L at all the prime ideals above P. They're all isomorphic. Because you just take some sigma that sends P1 to P2, and then you apply pure thought, and you realize that you've just convinced yourself that LP1 is isomorphic to LP2. So there we go. So let's look at decomposition groups. So now let's get back to, so here's the setup. As before, we have L over K, finite Galois. There, P as before, and P factors, P times OL equals P1 to the E1 times P2 to the E2 times whatever, PG to the EG. And all the E's are the same. But I want to choose P1. Let's just choose, let's just choose a prime of L above P. Let's set capital P is kind of P1, right? Some fixed choice of prime ideal of L, of prime of L. So you see what I've told you? I learned this proof in Marcus's book on number fields. I mean, I'm sure, whatever. Marcus number fields. I was on holiday in Crete when I learned that. You somehow remember where you are when you learn things. I know what a module was in the bath. I remember it suddenly dawning on me that I suddenly realised I knew what a module was. I was reading a T. MacDonald. Anyway, P is P. That's enough of that. Fixed choice of prime of L. So Galois acts transitively, and so we kind of want to understand this situation, and what we can see is that this Galois group is acting transitively on these things here. So somehow all the primes are the same, and there are elements of the Galois group that move from one prime to another. So what does this Galois group look like? Well, it kind of looks like G elements here, but then there's some other stuff. What stuff are we missing? We're missing all the stuff that fixes P1, right? By the orbit stabilizer theorem or whatever. This set here is isomorphic, bijects with gal L over K modulo the stuff that fixes P1. So if I want to understand this gal L over K, I'm really motivated now to consider this subset of things that fix P. So let's define dP to be the sigma in gal L over K such that sigma of P actually turns out to be P. I don't mean sigma fixes all the elements of P identically. I just mean that sigma of the set P is the set P, right? And so that means gal L over K kind of modulo dP is kind of bijects with this set now, right? So we kind of know what this, I mean, it's not a normal subgroup or anything. This is just some coset business. So somehow our task is to understand this dP, right? So this dP, what have we actually got here? This element of dP, if sigma is in dP, then sigma maps L to L, right? And sigma maps OL to OL, and sigma maps P to P. And now, again, by transport of structure, I get a map sigma from the completion of L at P to the completion of L at P, right? Fixing KP. Because you see, you kind of think, oh, I kind of need to do some calculation to check this, right? Because I've got some completion, and I need to check that sigma extends to some well-defined function on the completion. No, you're not thinking about it right. I'm saying this is obvious, right? Because LP was built by some algebraic calculation from here, and this LP was built by some algebraic calculation here, and this isomorphism identifies those calculations. So this is obviously true. You don't have to check that sigma extends by continuity or anything. You see, I'm telling you a magic way of, sometimes you can do maths for free. It's like category theory. So it's just somehow a tool. It's a tool, but you just sort of remember how it works. Category theory, when you're somehow, you know, some person like me that's not particularly bothered about monads or whatever. But you just use it. It's kind of a tool. Occasionally you can say some functor is representable, and it's just a nice way of packaging some data. Transport of structure is just a similar sort of tool. Sort of abstract, but once you've got the hang of it, you realize that it's giving you some stuff for free, in the sense that it's just saving you from doing the work. So that's kind of cool. Sigma maps LP to LP and fixes KP. And now what one can check, I don't think I'm going to do this, right? Turns out, so let me just do this. I've told you the fun parts. I'm going to skip the boring part. The kind of LP over KP is Galois, right? And that dP is isomorphic to gal LP over KP, there. And so that dP lives in gal L over K. And look at this. This is the local Galois group. So all that machinery from the first part of the course all applies. But I don't need all that machinery. All I need to do is I want to say there's an inertia subgroup and there's a Frobenius element. So this is some slightly delicate counting, right? So this is Serre local fields. Marcus doesn't cover it because Marcus doesn't ever talk about local fields. Maybe Fröhlich-Taylor. It's probably in there. Cassels-Fröhlich. Let's take it as a black box. If you put a gun to my head and ask me to prove it, I'm not sure I rate my chances, actually. But I did read the proof 25 years ago. So the upshot is that we have some fragmentary information about gal L over K. We have a subgroup, and that subgroup, yeah. So what have we got here? So gal So we start with gal L over K. So we choose our number fields L and K, and then we choose some prime P of the integers of K. And when we choose that there, next thing we have to do is we have to choose P, we have to choose capital P dividing P. And once we've chosen that, we get gal L over K contains dP, right? Which is gal LP over KP. So we had to choose a prime downstairs and a prime upstairs, dividing the prime downstairs. Of course, we could have just taken a prime upstairs, and then the prime downstairs would have been uniquely defined. So if you like, we're taking a prime upstairs, a prime ideal of the integers of L, and now we have this dP. So of course, gal LP over KP, this now contains some inertia subgroup, right? I. There. And the quotient of this Galois group by the inertia subgroup is generated by a Frobenius element. And now here's the fact, here's a global fact. It turns out this inertia subgroup is almost always trivial, right? If P doesn't divide the discriminant of L over K, the discriminant of an extension of number fields is a prime ideal of the base field. There's a slightly finer invariant called the different. The different is a prime ideal of the top field, but the discriminant is good enough for us. If P doesn't divide the discriminant of L over K, then this inertia subgroup is trivial. That's how it works. So L capital P is an unramified extension of Kp. And so it has a Frobenius element, right? And therefore, there exists Frob, let's call it Frob capital P, there, in dP, and that lives in this Galois group. So what we've done here is using our local theory, we've actually come up with an element, right? Here's an abstractly defined group, and we've chosen a prime ideal downstairs, and this is kind of really good. We've come up with an element.
Isn't that true for any finely extension fields?
What?
Like your global fact? Like I think it's true.
It's probably true in any situation where it makes sense. Yeah. But I don't know. It's just true. Yeah, sure. If I have if I have an extension of local fields, there's a local version of the discriminant. And the local discriminant is also trivial if and only if we're unramified. So this is kind of cool because we picked up some random element. But there's a problem with this, is that our element somehow depends on L over K, right? So it would be nice. You see, the problem is I can't change L, right? I've had to choose something upstairs. So it's a slightly annoying thing. Oops. It doesn't just depend on P, right? It depends on this Frob capital P. Maybe I should put what I'm talking about. Frob capital P depends not just on the downstairs thing. You see, because what I want to do is I want to, like we had that numbering. The lower numbering was kind of bad because it didn't behave well when we started changing L. And you can see there's going to be an issue here, right? If we start changing L, then I've got I've got this situation here. I've got K, I've got little p and K, I've got capital P and L, and now I want to change L to some bigger field M, and I want to see if my Frobenius element is compatible in some way. But M, like capital P, is going to factor into lots of primes of M, and which one do I choose? And there's kind of again some issue. So Frob P is kind of a bit annoying because it depends not just on the K. It's, I'm interested in K, right? L is some auxiliary thing. At some point, I want to change L into K bar. Okay, and then L is gone completely. But and I'll still have my curly P, my little curly P, but my big Frob P. So Frob P depends not only, not just on P, not only on P, but also on the choice of kind of capital P dividing little p, right? So let's say kind of P primed is another choice. So I've now got capital P primed. Here's the situation here. I've got capital P, it's P1. I've got capital P primed, it's P2, say. So I want to make another choice, and I want to figure out how those two Frob P's are related. And the trick is, by this global fact I told you that Galois acts transitively, by this global fact, right? By this fundamental fact, by transitivity, there exists some sigma in gal L over K such that sigma of P equals P primed, right? And now by transport of structure, we get that dP primed is going to be, there's dP, it's going to be a conjugate. That's the stuff that fixes P primed. So Galois acting on the left, so I better put sigma inverse here. P primed, that goes to P, that doesn't move P, and that puts it back at P primed. So that's going to be that. And I guess, and dP primed, and so sigma of Frob P primed times, well, and just the same thing. And Frob P primed, that element is going to be sigma times Frob P times sigma inverse. So this looks like an exercise, but it's not. It's just transport of structure. It's a triviality if you think about things the right way. Right? That, you see, what I'm saying is when I was your age, I looked at that and thought, oh, that looks like a calculation. I could probably do that. And nowadays, I kind of think, yeah, if I think about that the right way, I don't need to do a calculation. So I'm going to stop. But the point is, there's a conjugacy class. So the upshot, we can define Frob little p, yeah, different change in notation. I've had Frob capital P's. We can define Frob little p to be the conjugacy class of Frob P, of Frob big P, right? And that equals the set of Frob P primed for P primed dividing OL times P. So there we go. So that's what we have, right? And this works for all P not dividing the discriminant. You see. So in particular, it works for infinitely many P. So now this is kind of cool because this is the thing I wanted to tell you. So now gal L over K, we've written down a conjugacy class called Frob P. So in particular, we maybe haven't got elements, but you shouldn't really hope for elements in Galois groups. Hoping for conjugacy classes is a reasonable middle ground. Great. So now we have elements, and now we can talk about representations and traces and stuff, and that's where we're going. Have a good weekend. Oh, I'll be seeing you later today, but isn't it nice to have no more lectures for a bit?